Hi, everyone. I'm Abu Bakr, and I'm a PhD student at Northwestern University. Today, I'll be presenting our work on bringing logic-based intelligence to batteryless sensors. This is a shared work with Tosif Rahman, which was done during our internship at Nokia Bell Labs. Sensing has become an integral part of our lives. Smart sensing devices are used everywhere, from health monitoring to infrastructure monitoring and wildlife tracking. And the number of these devices is growing rapidly and is expected to reach 1 trillion by the end of next decade. Most of these devices are going to be battery powered. That means we will have 1 trillion dead batteries in a few years if appropriate actions are not taken right now. So researchers have proposed ditching these batteries because they need to be replaced regularly. They are costly and have bad environmental impact. So they have put forward the idea of ambient energy harvesting to charge small capacitors that are long-lived than batteries and using that energy to perform sensing and computations intermittently as the energy becomes available. And recently, embedded devices have become an attractive target for machine learning applications, as they are often connected to sensors that constantly gather information about the local environment. Today, most of these devices transmit sensor data to the cloud, which then performs predictions using a model such as DNN. This whole process costs a huge amount of energy to these devices. So there has been a lot of work on embedded machine learning that aims to enable local inference on these devices. And for energy harvesting devices, it is much more important to perform local inference because it is literally impossible for these devices to transmit the sensed data as they barely meet the sensing and computing demands. So the notion of intermittent computing for DNNs apparently seems pretty simple, but notice that the energy can come and go at any time, putting the programs and applications into a non-termination state where their forward progress is compromised due to frequent power failures. That means we have to save the program state by inserting checkpoints so we can restore from the same point and continue the execution. But for DNNs, the memory management required to maintain the forward progress is huge. You have to save all intermediate results before a power failure and restore afterwards. And on the other hand, batteryless sensors are supposed to be cheap so they can be widely deployed, meaning that they don't have much memory and compute resources, for example, floating point units or multiplication units, which are required by DNNs. So compilers support these operations in software that leads to inefficient code, which means the arithmetic-based compute of DNNs and their memory management would lead to high memory and energy overhead. So we ask these questions: are there any other better alternatives to traditional neural network-based inference algorithms for batteryless sensors? And what about logic-based inference algorithms? Because they are simple to implement without compiler support, as every general purpose microcontroller has these logic gates. And the inference on batteryless sensors is not that much sophisticated either, that the DNNs are the only solution. And finally, logic operations are energy efficient, so we can use them to develop some algorithms. So in the next 10 minutes, I'll be sharing an existing logic-based algorithm called Setlin machine, and then go over its implementation challenges and show how we solve them. And then I'll go give an overview of our implementation and share some results. So let's jump into it. A quick disclaimer: this is an existing algorithm. Without going into too much detail, I'll be giving an overview here, so the part where we make contributions become clear. Okay, so in 1961, Michael Setlin was exploring the use of learning automata to model biological systems, and he came up with the Setlin automata, which is a finite state machine with 2 end states. The first end correspond to one action, and the remaining state correspond to another action. These include and exclude actions decide if a particular feature will be used to determine the class or not. And these states can be transitioned using reward and penalty signals at training time. So if one automaton is trained for each feature in a particular problem, these decisions can be combined into some sort of propositional logic and used to infer the class. This is the basic, this automata is the basic building block of the settling machine. The next step is data preparation. The raw features are converted to Boolean features using a Booleanizer, which is simplified here. And then these Boolean features are converted to Boolean literals, which are basically Boolean features and their complements. These Boolean literals are then related to the settling automata using the clause computation unit. Here, the TAs include and exclude decisions, decide which Boolean literals are going to be used to compute the clause output. As you see, every Boolean literal here has a settling automata, and only 6 states are used here for simplicity, but you can use more if needed. Here, the first 3 states correspond to an exclude action, which outputs a 0, and the next 3 correspond to an include action, which outputs a 1. So this simple logic unit relates the input to the learned elements and outputs a single 1-bit value, the clause output. If we compare it with neural networks architecture, you will see that there is no multiplication with the weights, there is no summation or the activation function. Everything is reduced to this simple logic unit. So then these clauses are used to form a voting system. A class consists of L clauses, and it's up to certain machine designer how many clauses they would like to have in their system. The clause has a 1-bit output and has a positive or negative polarity, which essentially means if it is voting in favor of the class or against the class. So these votes are summed up together, and this is done for all the classes, and class with the highest sum will be the inferred class. So with this, we can put the whole settling machine together. Here is a multi-class settling machine that consists of M classes. Each class has L clauses with positive and negative polarities. And for every Boolean literal, there is a settling automaton. So the size of the multi-class settling machine is the total number of TAs, which is the number of literals times the number of clauses per class times the number of classes. One thing to notice here is that there is no data going from one class to the other because their computation is totally independent. That means if we are to checkpoint program state on an intermittently powered batteryless sensor, we would only need to store which class has been computed and which is not, and the class sum for each class, as we have seen earlier, which is just an integer. So we don't need to store a lot of intermediate results like we needed to for DNNs, and that is what makes settling machines most suitable inference engine for batteryless sensors. Now that we have seen the architecture of a TM, let's look at its implementation challenges. This is the clause computation unit that you have already seen. It uses input features and the include and exclude decisions to compute the output. Typically, to get higher accuracy, you need to have a higher number of clauses. This means we have to store more include and exclude decisions and do more compute, which leads to high memory footprint and latency. To give you a perspective of how this memory requirement explodes, take a look at the plots here. To get around 80% inference accuracy for CIFAR and a small keyword spotting dataset, we need around 4 and 2.7 megabytes of memory just to store the model. And typically microcontrollers don't have that much memory on chip. And even if they have memory, doing millions of accesses, memory accesses at runtime would take a huge amount of time. So in this work, we focus on encoding TM models to compress the model size while speeding up the inference at runtime to get better energy efficiency than their neural network-based counterparts. So we extract the TA decisions from a trained TM model and encode them. This compresses the model and makes it small enough to be deployed on a microcontroller, and then the microcontroller can perform inferences. Now, the key observation that we have made is that the exact state of the TA or the include and exclude confidence is only needed at training time. At runtime, we only need to know what the include and exclude decisions are. So if the model has some discrete values like this, they can be represented as binary include and exclude decisions. Secondly, the exclude decisions far outnumber the include decisions. So for example, a keyword spotting application with 10 clauses has an exclude to include ratio of 128, which means there are long runs of zeros and very few ones in a typical TM model. And we can think of ways to encode this information in a different way to minimize the memory requirements. For that, we have come up with a run length encoding based technique. I'll explain it here with an example. Suppose this is what our extracted trained TM model looks like. Typically, the microcontrollers are byte addressable, which means to store a binary value. The minimum container size offered by the hardware is of 1 byte. So your model would be of 39 bytes in this case. Well, you might ask, why use 1 byte to store a binary decision when you can represent it only by 1 bit? And as we have already seen, the models typically contain long runs of zeros and very few ones, which means we can use run length encoding to represent this information. So the encoded model would look something like this, and we add 0 in the start to know which number the model is starting from. We have found that this approach compresses the model by up to 99.3%. And since we reduce the memory accesses by 99%, we also get a speed up of 1.7x. For implementation, we used an MSP430 FR594 Launchpad, which is a standard platform for evaluating algorithms running on intermittent power, as it has a 256 kilobytes of non-volatile FRAM on chip that is used for checkpointing. For runtime system, we used an intermittent kernel that manages forward progress and keeps memory consistent across power failures. For evaluation of our approach and algorithm, we used vision datasets as benchmarks and keyword spotting as an application. And we look at the model size, accuracy, latency, and energy of TM and state-of-the-art binary neural networks. First, let's look at the size of the intermediate buffer, which is the size of the variables that are committed to non-volatile FRAM and read back at each checkpoint. As you can see, Settled Machines overhead is negligible because the computation of each class is independent of the other, as we have seen earlier. Let's look at how our run length encoding based compression works. We see that only few vanilla TM configurations with low number of clauses fit in memory, whereas encoding compresses the model by 99% and seems promising for using models with higher complexity that have more clauses and more classes. We also compare the memory footprint on MSP430 against BNNs. We find that vanilla TMs don't fit in memory, and encoded TMs have lowest memory footprint in most of the cases. And finally, we find that convolutional BNNs have very high latency. And also, as you can see here, with increasing number of clauses, as the accuracy increases, the latency goes higher and higher for TM. But notice that encoded TMs offer a middle ground between fully connected BNNs and convolutional BNNs, but with better memory footprint, as we have seen earlier. To conclude, we have seen that TM is a better alternate inference engine for batteryless sensor, and it can offer similar accuracy to BNNs. We have seen encoded TMs and binary neural networks have memory and latency trade-offs. Fully connected BNNs are most energy efficient, but encoded TMs offer lower memory footprint. In the future, we would like to explore new encoding schemes, as run length encoding might not perform good with alternating ones and zeros in the trained model. And we would also like to explore new applications with higher complexity and do some real world deployment. That concludes my presentation. I'm happy to take your questions now.